Graphically, this is what it looks like. It's hard to read the bottom here, but white oak, red oak, shortleaf pine, hickory, black gum, maple, and then here's ash, black cherry, and chinkapin. So that gives you an idea of what fraction of forest was there at Chinquapin. It was not a truly dominant tree, but it was one that was conspicuous in groves at a certain point on the landscape. Here's probably about the most dense distribution of pre-blight wood that I've been able to find. So this is what one of those groves would look like, 200 feet by 100 feet, and the skeleton's plotted, and then these circles are the actual canopy trees there today. The black dot indicates black oak. If it's not, it's white or post oak. And here's some samples of what the trees look like. Here are 4 typical plan forms of pre-blight Chinquapin as they lie on the ground. You can see there are the remains of these little secondary trunks, or whatever you want to call them, at the end. The fact that bayonet joints are really pretty common, and they often had fairly large lower branches. And then you find some unusual double, multiple stem trees, and a rare example where you had one that was killed by blight and actually continued to resprout, and the remains of those resprouts are there as well as they died back from blight again. But these are the exceptions, not the rule. Now, we were able to cut cookies to look at the growth pattern of a lot of these trees and indicate the size distribution as we saw them, and the height distribution as we inferred. And I've got a complicated set of criteria that we use to infer the height of a tree based on what we can cover. But the problem here is we're looking at trees that died more than 50 years ago. And the really important question is, how do you compare trees as they were 50 years ago with the forest as you see it now? So what we're going to talk about is trying to find some way to project the current forest back to the year 1955, and then put those dead trees into that forest and get some idea of how they actually fit into the scheme of things. Well, if we look at the tree rings, here's a typical plot out at Weddington. And for those who don't know the history of the Weddington block of forest, this land was acquired by the Soil Conservation Service as an experiment to see what they could do with land, with the poorest farmland in the Ozarks, to take it out of production and put it back into forestry. So the land was acquired in 1938, and of course, when people sell their land, they're going to want to squeeze the last dollar out of it, so we know it was logged multiple times around 1930 to 1940. And if you look at the oldest trees, you can see these release events that represent when it was logged. Here's the recruitment for the oak trees on that, the younger oaks as they came in, and here's the recruitment pattern for the Chinquapin logs we found. And you can see that this lives up to the advanced reproduction idea, the idea that these Chinquapins were small and suppressed, but alive before the cutting, and then when the forest was cut, they were released and would have kept on going like this, but ran into the blight. So we looked at small subplots of the forest, and here's a diagram of what that plot looked like, and the distribution of the various canopy trees, and the species identification. But the problem here is I've stood these Chinquapin logs up on end in the present forest as it exists, and it's unfair to compare these trees as they were in 1955 with the forest as we see it now, this being 2010. And graphic example, this is a reconstructed Chinquapin on a ridge top. This is the black oak that's there today, and this tree has something like 55 extra years of growth compared to this one. So you really can't compare them directly. You have to do some sort of reconstruction. reconstruction. Well, how do you project a tree back to what it was like 55 years ago? And the scheme I used was that this is a resource allocation problem, and the solution to that differential equation is an exponential growth curve. And you can characterize that by an amplitude and a curvature of the growth. So coefficient A is the amplitude, coefficient B describes the curvature, the exponential decay as you go back in time. And the question is, how do you figure out what these parameters are? Well, my rationale was that this forest has always been a forest at Weddington. It's been selectively thin, but it's been a forest, and so all of these trees have been growing up into the canopy just as they are today. So my working hypothesis was that the diameter distribution versus height in the forest today probably approximates the diameter distribution versus height in the past. So we start from the fact that we know how tall a tree is today, and we know what its diameter is. And we have one other data point, we know that at some time in the past, we don't know when, it had no height and no diameter. So the real question is, how does it get from point A to point B? It's probably not a straight line. It has some sort of curvature, but does it curve up quickly, or more slowly, or something in between? And the red curve is going to turn out to be the curve we want to use. But how do we get there? Well, what I did was look at all of the heights versus diameters of the trees and see that they formed a trend like this, and that this curvature of the red line goes right through the middle, and the same curvature going to a different amplitude pretty much encompasses the higher and lower ends of this envelope. There's some outliers here, but we expect that because there's been an ice storm that's knocked the tops off a lot of trees. So the conclusion is that this curvature describes the height versus diameter growth for the trees in this local forest. So here's what came of it. Here's the forest as we see it today, approximated the pre-ice storm shape of these trees by these dotted lines. We cord each one of these trees and figured out what their diameter was back in 1955. So the question is, if we know what their diameter was, what was their height? And using that curve, this is what we constructed, and you can see that the Chinquapin tree is part of the canopy. Even though it looks to be a little bit smaller today, 55 years ago it was as big as any, or bigger than any of the other trees in the area. Same thing for another plot. The forest now with the Chinquapin stood up, the forest then with the Chinquapin fleshed out, and you can see these trees were, these Chinquapin trees were canopy dominant trees at that time. So what can we conclude about Chinquapin in Arkansas? It was widespread and locally abundant in groves, comprised just under 1% of the upland witness trees, about the same as white ash. The average density overall was only about 1 per hectare, similar to white ash. Blight arrived in 1957 and just mowed the trees down. It preferred the top of slopes on tree soils. So not necessarily the exact ridge top, but the edge of the ridge top as it wound around the landscape. It once reached 40 centimeters in diameter, which is like a 1.5 feet, and would have been bigger if it had time to become as mature as trees are today, and was at canopy height of 15 to 18 meters, 60 to 80 feet. We predict a subcanopy tree with spreading and crooked form when the forest matured. The living sprouts loosely cluster around the former seed source, and that's actually different from what I found for chestnut. In the case of chestnut, the seedling sprouts tend to be located away from the trees, and I suspect that's because chestnut was such a sought-after nut that all the animals would plow 100% of the ground under chestnut trees themselves, looking for the nuts, and they would only escape if they were buried far enough away to make it not fully worth their while to go after every square inch of the ground. So that is a difference. The living sprouts seem to be associated with the seed source directly. Very few of the large trees were sprouted. In the case of this reconstruction, only 2 of 108 were found to have shown any signs of having resprouted after being killed. Living sprouts are probably almost all old seedlings and not associated with the presence of big trees. And the tree form denotes disturbance history. I didn't show it, but almost all of these 108 trees had a single dominant stem. Whereas we know the trees that are repeatedly burned tend to develop these multi-stem forms. So the fact that almost all of these trees had single stems tells me that fire wasn't very important as they were getting started. Now, of course, that puts them back in the 1920s at the age of heavy fire suppression. So that makes sense. But these trees tend to evolve a single stem if they're kept free of disturbance. They develop these multi-stems if they're damaged by farming equipment or logging equipment or burned to force them to come up into these multiple stems. So that's a story of my chicken study. It was published in 2012. And if you give me your email address, I can send you a PDF file of the actual journal article, if you're interested.
Good photo, Fred.
And I'm actually sitting on a Chinquapin log. That's out of Weddington, and those are logs that are a little over 1 foot in diameter, and they are completely solid. Okay, any questions? Yes?
Just how, well, a tree got to be about like 2 feet in diameter. Do we have any idea just how old they were at that time? Just how old do these things get?
Well, that's a good question. The trees, I guess, looking at the cross-section we got, none of them are older than 100 years. They had this typical chestnut-type high growth rate. And the only problem with that is the trees in Arkansas were largely cut away in one big lumbering operation around the turn of the century. And so most of these Chinquapins were still rapidly growing in their youth. And we don't have any older samples left around to look at. The other interesting thing, I don't remember that tree that I showed the release pattern of. Let's see if I can get back to it. Yeah, this one. Notice how the wood is separated here. That seems to happen with a lot of Chinquapins that we section. When you have these heavily suppressed trees that suddenly get released, when the tree is died or is killed, the wood tends to separate here, and so we have a lot of these old trees that show this rapid growth record, and then the center is missing, sort of rotted out because water got in there. And I suspect that a lot of them have these centers of extremely slow growth, maybe even 100 years of suppression. We don't get to see that because water got in here, and if you read my chestnut work, you'll also notice that American chestnut logs from pre-blight also tend to have a hollow, rotted out center. And that isn't by accident. What happens is that, you know, that younger wood is actively conducting wood. It's got open vessels that are carrying water. But as the wood gets older, the tree plugs it up with resin and kind of abandons this core. And the interesting thing is that resin actually makes water stay in the wood. And so the centers tend to rot, even though the tree is rot resistant. The centers rot because they retain water, whereas these vessels out here allow the water to drain out and let them dry out immediately after a rainstorm. So the bottom line to your question is that the bigger Chinquapin logs per section all were hollow on the inside, and we really didn't know what their early growth history was like. as far as I can tell, we haven't seen anything that's much more than 100 years old, even though they're a couple feet in diameter. All we know is the outer part of the tree was going to be bad in a young forest. Yes, John?
It's not exactly related, but you might know this quick answer or point me in the right direction. Has anyone done, to your knowledge, any reconstruction of like chronology based on palynology of the Chinquapin? I ask this because I know where there's potentially some sources where pollen could be captured in somewhat.
Well, it would, as my knowledge, no one has done it, and I've looked at the pollen records, and the only place where I can find a lot of pollen, castanea pollen, not being enough to be more than a trace, is a bog near Austin, Texas, from the end of the Ice Age. Like the Boreac bog. Otherwise, you see a chestnut pollen grain or two here and there, sort of randomly in places like cupola pollen, but it generally flies below the radar. And for those that don't know about palynology, one of the problems with North America is almost all the records only begin at the end of the Ice Age, whereas in Europe they've got pollen records that go back millions of years. One interesting result is that about 2 years ago, a pollen record for the past 130,000 years was published for North America from a site adjacent to Mount Vernon in Virginia. And it's a very interesting pollen record. It's beyond the modern range of chestnut out on the coastal plain and has no chestnut pollen in it. But it's a really bizarre record in the sense that most of the time since the previous Ice Age, 130,000 years ago, the area has been extremely arid and mostly just jack pine and black spruce. And if you know what the climate in Washington, D.C. is today, it's quite different.